Thanks everybody for coming. My name is Sergey, and today I will be giving a talk, a short talk, I guess, about the programming microcontrollers. So just before I start, I just want to get some feeling about the audience. How many of you has been already working with micros, programming micros? Please raise your hand. Cool, thank you. So also, I want to say straight ahead, I'm not an expert. If I tell bullshit, please correct me, right? So let's start, I guess. I'll start from a little bit of history, how it all began. Some time ago, actually a long time ago, people who created electronics, they were making a piece of electronic for each specific task. Now these pieces of electronics they called ASICs. I think you've heard the term. It's a application-specific integrated circuit. So it's basically a piece of an integrated circuit that does some specific thing in the hardware. So people have like special tools to design such circuits. And the end result is basically a specialized thing that just does only that thing and nothing else. So for example, in military they use electronics for image recognition. There are specific ASICs for Bitcoin mining and things like that. So this thing is basically built-in hardware. Hardware does that some specific logic. And there were no microcontrollers, no microprocessor, nothing. So that was year 1969. A bunch of engineers from a company called Busicom, I think that's the right spelling, from Japan. So a bunch of Japanese guys came to the States, to Intel, asking to design a specific chip for their calculators. So I guess what was happening is that it was some sort of, I'm guessing here, it's not a fact. That is a fact that the year 1969, a bunch of guys from Busicom came to Intel. I'm just speculating. So Intel was like into the integration project for Busicom, developing the chip for them. And then the guy in Intel called Martian Hoff had an idea of how to do it differently. So not like the way everybody did, but basically create. So his idea was to create a chip that didn't have a specialized calculator logic inside. So his idea was to create a chip that would be able to do anything, basically, all sorts of things, and put that calculator logic as a program inside that chip's memory. So that was his idea, which we know what it is. It is a microprocessor plus memory, but up to that point, nobody had that idea before. So there was a fight that usually happens inside the company, and his idea somehow won. And they hired a guy called Federico Fagin to do this stuff. He was like heading the project. And sometimes later they did that. So that was actually how the first microprocessor was born. So Intel was much into that idea. Intel realized the power of this thing, and they kept developing it even after this project was over with the Japanese guys. And Intel bought the license from them. So basically, the idea of the microprocessor was originally the property of this Japanese company, and Intel bought it from them. So I guess Japanese company didn't realize what the treasure they were holding. And so after they bought the license, they released the first microprocessor on the market, which was Intel 4004. So at the time, it was something absolutely breakthrough. So this thing, I don't know how much memory it was able to handle. It was a 4-bit processor, so 4-bit, and it was able to do 6K operations a second. Later on, a big American corporation, CTC, ordered a bunch of those microprocessors, and together with TI, they went on to enhance it and develop it further. And the result of this collaboration was the Intel 8008. So 16K of RAM and 30K operation second. I think it was able to handle 40-something. It had 40-something instructions. So CTC, I think CTC dropped from the deal, but Intel and TI still progressed. And Intel basically released this first 8-bit CPU, and then 2 years later, the 8080, it's a famous thing, everybody knows about this. So year 1974, they released 8080. So this guy, and it was kind of like a de facto standard on the market. Everybody was trying and making programs for that CPU. But the other people didn't sit idle. So a fierce competition started. So first of all, a Motorola competition, and you see, so that this first processor, originally when they released it in 1974, it cost $360. So dollar at that time was a bit more than it is now. So it was a pricey thing, one single CPU, 360. All right. So a bunch of other companies started to chase Intel. So Motorola was one of them, and famous processor 6800 by Motorola. So they developed it and pushed it to the market. And a few others. So few others was the company called MOS. Don't remember what it stands for. So they developed this guy 6502, a microprocessor. And the company called Zilog. It's an interesting story. In 1976, 2 years after I-8080, the guy, Federico Fagen, who was heading the first CPU project by Intel, this guy. So this guy who implemented the idea of Martian Hop, he quit Intel and started his own company called Zilog, and he created Z80. So, and the Z80 was one of the biggest commercial successes. So that processor was in tons of computers. So basically, these three guys were dominating the market. They actually beaten the Intel original, and in late 70s and 80s, they heavily dominated the market. An interesting thing happened in 1975. So in 1975, there was a big conference in the US called WestCon, and actually all the big companies were exhibiting their stuff, including Intel and Motorola. So they had their microprocessor sold by 180, roughly 180 a piece at this conference. And a company called MOS went on also to this conference and announced that their microprocessor was $25. And it was like...
I think MOS was actually founded by the guys who created the 6800 as well.
Exactly, from Motorola, yeah. So the guy from Motorola quit,
Yeah.
joined MOS, and then they had some like patent or whatever issues, yeah. So they announced like $25 thing, and Motorola, they went furious, and they immediately they dropped their price from 180 to 70 at that day. So basically, that shows like how diffuse competition was and how like people were like aggressively going to the market. So that is roughly a microprocessor story. So how does it come to microcontroller? So this is the microcontroller part of it. So year 1970. So remember that the microprocessor work began in Intel by the request of this Japanese company to work on the calculators. And the work on the microcontroller in Texas Instruments started in year 1970. I haven't found anywhere in the books or in the media what was going on, but it just looks weird. So I think what happened was that maybe Texas Instruments they were fighting for this project basically, and I think they started parallel project on their own to implement that idea. So basically, the guy Gary Boone in TI, they created the first MCU, so basically a chip that is able to fully implement calculator. So I believe, that's my speculation, is that they were actually implementing one of the, calculators were like widespread at the time, so they were just making a piece of hardware that was able to implement any calculator quickly. So, so these are the parameters of this like breakthrough thing. So what is the micro? So in short, the microcontroller is a computer. So microprocessor is a heart of the computer, is a calculation unit. So it's a thing where you have like many like legs. You put like instructions in, and it basically executes instructions. That's pretty much it. Microcontroller is also called you can find like in the literature MCU, microcontroller unit, or UC, so that's microcontroller. So the microprocessor itself is not useful much because it cannot do stuff on its own. It needs to take instructions from somewhere and data from somewhere, because instructions, they usually reference data. So you have to have at least memory, a piece of memory attached to the microprocessor. Also, the results of the computation should be somehow sent somewhere, either in memory or like to the external world, right? So basically, a microprocessor, in order to be a proper computer, it needs to be connected with at least some peripherals, right? And so these peripherals are implemented in the electronics as a standalone, like a separate circuits, like integrated circuits. And they could be connected to the microprocessor. And these circuits, they call input-output peripherals. And for the I/O peripherals, there are many different standards. So you probably heard about at least this serial communication standard. So that's the serial port. Pretty much every computer in the early days, they have serial ports. Now, USB standard, and like even today I'll be using USB to serial conversion. And many others like I2C, SPI, and so on. So basically a microcontroller is a small computer that has it all. It has memory, it has peripherals, it has like power inputs, and it can do a naked microprocessor cannot do things on its own, and a microcontroller can. So, and the beauty about the microcontrollers is that they are cheap. So these are the cheapest computers that you can get. So the prices vary very widely from basically cents to dollars and dozens of dollars. So it depends on, there are huge variety of microprocessors. But at least to give you an idea, typical MCUs, they cost $1 or a couple of dollars. So that's price tag. So this is the image, a typical image of a microcontroller. So it has memory, RAM, ROM, a processor itself, and the peripherals, like a AD converter. It could be I/O ports, and so on. So the big thing is if you take the microprocessor, so the big question is how does the microprocessor controls the hardware that is attached to the processor? So the answer is that it does it by setting or by handling two types of registers. So the first type is the core CPU register. That register is in the design of the CPU itself. Like for example, on Intel, there are registers like AX, BX, CX, or whatever. So a bunch of registers. Some of the registers, and all the registers have functions, right? Some registers are general purpose general purpose registers. Some are not. For example, a stack point register is not a general purpose thing, so it has a special purpose. And there also could be a specific hardware control registers. And the other type of registers are what they're called hardware registers. They are memory mapped. So basically, the external memory that microcontroller has, the memory management treats special addresses in a special way. For example, the designer of the microcontroller can say, okay, the memory location, the byte at the address 10 is responsible for setting the clock of the MCU. If you write 1 there, it will be one value. If you write 2, it will be overclocked. Something like this. It's just an example, right? So it's basically it's a special memory location, or like it's in the old DOS, there is an interrupt table at the beginning of the memory, and there was a video area, and so on. So if you write in a special location, that was going to display, right? So similar things. So special memory locations that they are really used for hardware control. And so this is an example. Sometimes they even have a special name, SFR, Special Function Register. So CPU has an access to that special register, and by writing bits into that register, you can control the hardware. You can say switch on and off relays and things like that. So, and the hardware registers again. So you can set up the speed of the communication by writing some values and some specific address. And all these things are documented in the datasheet. So the datasheet is the documentation piece that is provided by the MCU manufacturer. So, and for those who work with specific MCUs, I guess that's the main authoritative source of truth, the datasheet of the MCU. So again, the microcontrollers, they are tiny. So and the development of the hardware product and microcontrollers are usually used in some hardware products like watches, wearables, all sorts of things. Like pretty much every car these days have like hundreds of them. Like I guess 200-300, something like this. Pretty much every function, like controlling windows, controlling anything, is done by some specific microcontroller inside the car, and like the central computer drives them all. In your home, I guess there are a couple of dozens of microcontrollers, like thermostats and things like that. If you have like maybe like kettles or like washing machines, stuff like that, they have microcontrollers inside. So people use microcontrollers to make electronic products, and the process of doing that is like really complex, is elaborate, is long. So first people do prototyping, and they go into hardware design. They write firmware for the microcontroller. And like the whole line of product development, designing the the case, how it's doing certifications and things like that. So it's like really long and complex. But the thing is that the microcontroller itself, they could be like large enough, or they could be tiny. They could be like small. So this is like an example, like a small microcontroller. You cannot really use it directly. So in order to wire it, even like connect like power inputs to your whatever power, and then connecting say few legs to an LED to light it on, it's a challenge because like it's really small. So it's not usable to actually work in a development environment with a microcontroller itself. People don't do that. Instead, they work with development boards. So companies who produce microcontrollers, and not just these companies, other companies as well, they develop a development boards. So it's like a printed circuit board with a microcontroller on them. Like for example, this is Arduino Nano. So it has like Atmel MCU. So, and they are specifically designed to make it easy to work with them, to program them. So for example, this board has a USB input, so you can stick it in your laptop and like flash programs on it, and it will power as well. So it's a USB input. And this is an example of the board from STMicro. So the difference is that this board has huge number of peripherals on it, like TFT display, all sorts of many other things, many timers, many GPIO lines, and so on. So people use, for development and for prototyping, they use development boards. So it's much quicker to do programming on them. There is also something called something in between. The people call it module. So sometimes manufacturers, they develop so-called modules. It's a microcontroller with extra bits of peripherals on a single printed circuit board, which executes some specific functions. So I'll show you now. Development board called a node MCU, which uses a module. So a module, this is a certified chip made by like specific vendor with the microcontroller and a bunch of peripherals. In this case, it's the peripherals is extra flash memory and external Wi-Fi antenna. So the module itself, it plays a role like a plug-and-play thing. It can do Wi-Fi, basically. So you can take a module, stick it in your design, and it will work. So many boards have modules on them, and many just microcontrollers. So this is an example of ST micro board. This is the microcontroller. It's big, right? And the development board has like tons of peripherals, and tons of output, and so on. So when the prototype looks good, people, people design the printed circuit board because in a specific product, for example, you're working on a watch, right? On a watch. On your watch, you wouldn't stick this huge board inside, or because it's for development. So what you do, you would create, design your specific printed circuit board, a PCB, and special people, hardware designers, they design a PCB. So they use special tools to create this PCB. They take a look what components to put, how components work with each other, are they cheap enough? They optimize for many things, for space, for price of the end product, and so on. It's a complex process. These guys are really, the guys who can do the proper PCB design fast and without mistakes are invaluable. Because a mistake in a PCB, it costs a lot. You make a mistake, and then you have to like redesign it and like print again, and the turnover is long. So it's very, very crucial part of the process to create a PCB. But basically, the PCB is actually the heart of the electronics that goes into the end product. And usually the MCU is the central, is the core of it. But the firmware is usually developed on the development board. So on the development board, people, what they do, they recreate, this logic and this setup, the end product, in a development form. They just stick things inside, and then all the sensor or peripherals they want, and they develop the firmware on the dev board. And then later on, when the PCB is ready, they start testing on the PCB. And there is a video. I think you might take a look at the example. Let me see if it works. I don't think it does. Does it? So this is an example. The result of the PCB design is a special set of files called Gerber files, and a special tools called PCB printers. It's kind of like a 3D printer, but way more complex. They take like a piece of how do they call it? Like I don't know the English word for that. But basically, then a special tools goes and creates all the paths on the board, and then in the printing houses, what they do, they take all the components and like put and solder on top. So it's a long video. I won't play it all, but you can see it basically goes and creates the whole thing according to the design.
What is that? Glue? What is?
I believe this is this is some sort of a glue, and then the whole thing is put inside a ASIC and it got etched, right? So that's the process.
That should be for prototype only, because it's just one layer.
Yeah. It's a prototype. That's a prototype. Usually, like the the real world PCBs, usually they have like more layers, and the machines that do that, they don't look like this. It's a prototyping printing machine. Usually, these printing machines are really like printers, but they do not have cartridges with ink. They have cartridges with the peripherals like LEDs, sensors, even shops that sells those peripherals. They put the price like for one piece, for 10 piece, and then for the whole reel. So they have like a huge reel. You can buy the whole reel, and that goes directly inside this printer. And the printer, you like literally charge the printing machine with all these peripherals. It like etches the PCB and then solders all the components on top of them. So,
isn't that later in the process? I mean, I think you have the PCB ready, and then the machine it's a pick and place machine that picks the components and
yes.
puts it there. It happens after the PCB is printed, then like the printed PCB, I think it's an input to that machine.
Yeah, well, I think of it of the whole process like a printing, printing PCBs. And these there are companies that do that, printing houses. There are a couple of in Ireland, by the way. On Limerick there is one, like usually there.
Nowadays, the most of the PCBs have 5 layers, so it's not printed like that way. 5 layers.
Yeah, so
that's the cheap one.
So this is the process, and this is the an example of the end result. Like the printed PCB with the controller on it. All right. So basically, what we see is that the development board is the main thing in the development environment, and the crucial thing is just to get the datasheet from the manufacturer, set up the development environment. And usually every controller vendor provides their own SDK. But in this example, we will not be using the SDK, we will be doing the bare metal programming. So a very basic bare metal example, which even doesn't use the standard library. It's like bare bones, talking directly to the hardware, not using anything. The traditional and embedded programming, the traditional program that people use or write first is called Blink. It's not like a hello world in the usual programming, because there is nothing to write this hello world on, right? Usually it's Blink. So the development board usually it has an LED, a light. And the program, the first program, just blinks it, periodically. That's the first hello world, and that's the standard kind of. If you're in embedded programming, the first thing you do on you controller, you do blink. So that's what we'll be doing, and I guess at this point I'll switch to the just show my screen, and I'll describe the layout of the environment and the program itself. So it's like I try to put it like as small as possible. So you can see this is one piece, the assembly part, the bootstrap. This is the main C program, and that's it. So that's it, nothing else. And the make file just says how it's built. So I'll show you how, so as you can see, it's like really a bare minimum. I don't know how, can you strip it further? Maybe you can, but this is what I got. And I'll be using the board from ST Micro. the one that I was showing there. So it's like a big board with tons of stuff, with a TFT screen and other stuff. But we won't be using any of those. I'll just be using like a tiny green LED on the side, so it will blink. Hopefully, if it works. So this board is equipped with the serial port, with a USB port. It has like onboard serial to USB converter, and through this you can actually power the whole board, and also you can flash it. So you can develop the program on your computer, and then through this USB link you can transfer this program to the microcontroller. So that's what I'll do. I'll connect it to the thing, and let me thank you. Yeah, so yeah, it's blinking because I did it before, right? So
Cheater!
I was preparing. That's what I usually do before coming to the meetup. But okay, let me show you the structure of the whole thing. So first of all, before like doing any programming, what you do, you download the datasheet. The datasheet, in my case, the development board is like STM-F4 line, right? This is a line of processors, of controllers from a company called STMicro, a French company. And what you do a Google search, literally TRM STM44F4, and that's it. So the first link is usually the PDF. This is the PDF, I've downloaded that. It's huge, right? It's, how many pages? 1,745 pages. So it's really huge. But basically it contains everything about the microcontroller. But this TRM for the microcontroller is a specification documentation for the microcontroller only, for this like box, black box. But there is also the development board, which has extra peripherals like this blinking green LED that blinks. So I have to know which pins, which like one of those connectors, this green LED which is blinking is connected, right? So I need another piece of manual. So you do Google, the exact version of this board is called STM32F429i. You Google it, the first link will give you this document, this one. So, and in this document, you'll find that let's do that. So I'm searching for LED, right? LEDs. Can you see that, by the way?
Yeah.
Okay, LEDs, page 17. I skip to page 17 and I see that I want to blink some LEDs. So what choices do I have? I see, okay, LED 1, it's like red LED status for the power and so on. Usually the LEDs that under your control is called user LED. So I see that green LED is the user LED connected to the I/O PG13 of the STMicro, right? So now I know that the I/O port PG13 is my LED. That's what I should control. Okay. I know a little bit the architecture of ARM already, so I know a little bit what to do. But basically, the PG13 is a special pin on the port G, on GPIO port G. So what I know now is that I have to enable it and then turn it on, spin, turn it off, spin, turn it on, spin, turn it off, spin. So basically enable it, set it up, then in infinite loop, just turn it off and then do like a busy spin in the processor and turn it off. That's it. When the ST microcontrollers, when they turn up, usually they have, to save power, they have all peripherals disabled. So the oscillator clock is disabled on all them, on all of them. So, okay. So before, actually, let me go back a little bit. So this is a. Can you see clearly, or should I increase the font? All right. So this is the structure of the whole project. So you can see that there are actually just three main files: bootstrap.s, the link.ld, and main.c. So these are three files in that minimal setup. And the tools that I use, there are only two tools that I use. First is the GCC compiler for ARM. So, and the second one is the ST-Link utility to flash the program to that thing. So I don't remember what the brew. So on my Mac there was like a brew command to install those. So it's just the two programs to be installed, and then after this you can basically program and work on the ST micro boards. So if you open, yeah.
You're saying that this command S-Link, you think it's kind of you can use it to flash all
Yeah. Not to any, to ST microcontrollers that have a special ST-Link circuit. They have like enabled that. They have like their own special ST-Link hardware. And this program basically works with it. So not to any, right? For other microcontrollers, there are other utilities, other programs to flash them. For ST controllers, there is ST-Link. So, and this is the technical reference. So we know that the LED that we want to turn is PG13, and that's the only information we need from this panel. So we can basically close it. We don't need it anymore. And this huge manual, huge data sheet, it's like enormous. But we won't be studying everything. We'll just find out the relevant bits. So first interesting thing is the memory map. So if you click on memory map, is it memory map? Okay. So if you click on memory map, this memory map will actually describe the whole. It's just 3 pages. It's not huge, but it will describe you. Remember, I was talking about the hardware registers. It will describe these special areas of memory that have special meaning. So, for example, we know that our LED is connected to the pin PG13. So we know that GPIO G is here. So we know its base address of the GPIO. We know that our LED is connected to this bit. And for example, if you work with TFT, you know, by writing and reading special memory areas from these locations, you will be able to like work with the TFT display. You can click on this like link, section 16726, which I believe is huge, and it will describe in detail how to initialize TFT, write to whatever pixels, letters, and so on, right? Set the brightness and all that stuff. and the same for all other things. Like you see that there are RNG, random number generator, so you can generate numbers on that chip, or like hash, crypto modules, and so on. We won't be looking at those. All we need is GPIO-G. So how do we enable the clock on the LED? By operating on the RCC register. So where is it? It's called reset and clock control. So RCC, and this RCC register. So basically this register, it says how to enable a clock on different peripherals. It says the RCC clock control register, the offset is 0. The memory table, which I showed before, it was showing the base address. So on the offset 0 of the base address, this is the description of all the bits of this register. The register is 32-bit. So if I scroll down, I'll see that, or is it? And we need the HB, I guess this one, HB1 peripheral clock register that sets the GPIO. Yeah, so this thing, it basically, this register controls which GPIO ports are enabled. So we need PG, so we need GPIO G enabled. So in this case, this is GPIO G enabled, so this one. So basically, I'm just showing this just to let you feel how it takes for the newbie to start doing that. So if you open the main.c program, so you can see that, okay, so the base address of the control register is this. I just copied that from Datasheet. Can you see that, by the way?
Make it bigger.
All right. So basically, this is a copy of the reset control register, and so in the program, what we do, we see that this register. You see that the
Can you zoom out a little bit, please?
address offset is 30 hex. Let me see if I can do this.
Is it plus on the top left-hand corner, or a little magnifying glass? Yeah.
Yeah. So you see that the address offset is 30 hex. So 30 hex, but we are using 32-bit words. That means like 12 words. So that means that this line 14, it sets the hardware enable bit in this register to, it enables bit number 6. So port is 6, that's G, GPIO G. GPIO A is 0, A, B, C, D, E, F, G. G is 6. Right, so basically this thing, this line, sets the bit, where is it? This, bit 6. And it says, this bit sets and clears IO port G, clock enabled. So basically, this light enables the clock on the LED. So am I saying that clear or not really? Okay, just ask me a question if it's not clear now. So later on, then where we go? We go into description of the GPIO. This is the general purpose input-output. That's how the LEDs are working. So LEDs are connected to the GPIO ports. In this case, PG13, and we specify special bits into on that register. So on PG13, so we set the mode to be GPIO mode. We set the speed of the GPIO pin, and we set the push-pull output. I won't go into details. What does it mean? It's like special hardware-related stuff. But basically, what we are doing is we are setting bits on 3 registers that are responsible for LED. And the way you find it in the datasheet, you go and you find the GPIO. Where is it? DMA. Somewhere should be GPIO registers. here it is. So general purpose I/O. You go to I/O registers, and you find a description of all the registers, like register mode, which sets. So we are setting this to general purpose output mode, number one. The speed and the type. So I'll probably skip that. It's not that interesting. So that's basically how it works. So you see what we are doing here. We are working with the memory locations. So we are not doing anything like a black magic. We're writing bits to special memory locations according to the datasheet to set the hardware in the way we want. So basically, these 4 lines. The first line enables the GPIO port where the LED is connected to, and the next 3 lines they set up the LED itself. And then what we do, we just enable the LED, so put the voltage high on this LED, then we loop, busy loop, like a bunch of cycles, just to provide a delay, and then we reset this bit. So we turn the LED off, and then again we loop, and we do it in the infinite loop. So that's basically what we do. So in this case, you see that this is
the 16 magic number.
Where 16. It's so if you look at the BSSR register. So here it is. So GPIO set and reset register. So you see it's divided into like high nibble and low nibble. So low. So every. So you what you do. You are resetting by setting your, say, we are PG13, so our pin is 13. So we set the 13 bit this way. Like by writing here, by writing 1 here, we turn it on, and by writing 1 here, we turn it off. Right? That's the way it works. So so this is 13, and this is 16 plus 13, right?
Okay. Is there some mechanism that turns the other one to 0 if you try to reset them?
Yeah, it says that if you write 1 to 0.
So they're paired.
The documentation usually says it. Should you reset the other bit or you shouldn't? The ST micro says you should, which you just you write, and that's it. So and it's all write registers. You see, they could not be read. It's write. So when you're writing, the hardware intercepts the fact that you're writing with a special address, and I need to reset the pin, put it low, so it put the low voltage on the thing. Right. So that's how it works. And do nothing.
Oh, really?
Yes. Yeah. So I can show you if you because otherwise the optimization kicks in. It will just removes that loop, and you'll be setting and resetting in the busy loop. Everything, so it won't work.
And the second question is, do you have some timers that you could use instead of a busy loop?
Well, honestly, in the real world, like this is just a toy, right? So it's like a single thread one. It's like Arduino programs are like that. So if you ever work with Arduino, they are like setup and loop, right? Which exactly mimics this logic, because Arduino guys designed it specially for people like makers that do that sort of thing. But when you are doing complex stuff, when you need to do like network operation, you need to like handle interrupts, user input, all that stuff, you need a proper multitasking, I guess, OS, timers, and so on. So the real world thing doesn't look like this, right? So it's like a proper program with tasks and so on.
No, but I guess what I'm trying to ask is if people would busy spin all the time, or would they prefer some sort of timer approach?
For simple stuff like this, yes, man.
Okay.
If you look at the Arduino programs, like delay, whatever, it's like all over the place, everywhere. It's okay. If you have just only one task, why not?
there must be other tools or loop that you can wait for the processor without looping and without consuming energy.
Yes, right. Yeah. Usually, like what you need to do, you need to like specify a timer and say, okay, wake me up at this point. But setting up a timer is like digging into Datasheet for hours, then writing code, it doesn't work, what the hell, and then you debug it, and debugging this thing is not easy, right? You don't have like a nice, actually you do have a nice GDB, but anyway. So you will go like look forums, example programs, see what's going wrong, and then, oh, my like interrupt handler is like does something that it shouldn't do, that's why it doesn't work, or it kicks in just once, not the second time, what the hell. So, and it's on and on and on, you know, it's the usual stuff. The problem is that a microcontroller programming is a bit different from the usual one, because it's sometimes so tied to hardware, you can get problems, the hardware-related problems. Like, for example, like your Wi-Fi link is like, you know, like weak, and sometimes uses because in your PCB you put the antenna close to some other circuit, so when you have like a big number of like user inputs, your Wi-Fi, you know, is not working properly. That sort of problems, or you didn't pull like you didn't set the set up the pull-up register on GPIO, and it's floating and sometimes gives you like random results, stuff like that.
I didn't use electrostatic bracelet and you're just touching it.
Yeah. So things like that. So usually people who do work on the microcontroller programs, they also know a little bit of hardware. They know what is going on. Sometimes they're like really good people, and they, like, for example, I was working with a guy who was working on a project. Basically, a customer requested the device reset when you consequently reset it like 5 times. So you reset it 5 times quickly, and you should factory reset the device. And that was like to be implemented, but how? We didn't have any extra memory to put the fact, you know, to write down the fact that we, you know, reset a second later. Because you reset everything, and clock as well. How do you know that you just recently reset? You start up, you don't have even a clock to know that you reset just half a second ago. So how do you do that? You could, well, there are different ways to do that, but basically he came up with a simple, you know, with a like a resistor and some capacitor, who was like losing power very fast, and this like capacitor or a couple of capacitors, basically he created a 4-bit memory cell, something like this, in just few hardware components that were able to hold the fact that I was just reset about like half a second ago, but just for half a second, right? And basically that counter was incrementing, and if it was like above 5, you factory reset. If not, then it's not. So that kind of stuff. Without a hardware knowledge, it's really hard to do these things. But if you do, the value of such a developer, it increases enormously, just enormously, because it's a really rare mix where somebody knows hardware and the software. And believe me, software problems that are used to, you know, appear in that sort of environments are sometimes really tricky and interesting as well. So basically, I guess you get an idea of how this like simple blink works, and yeah, it works like this. Also, a couple of things to be mentioned. So first is the bootstrap program. So this is main, right? So this is called main. When you compile this program, the compiler creates an object file with the main function. But something has to call this main function. So who calls this main function? In your usual operating system, we know who calls that main function? Do you know? Do you guys know?
Start.
Start, yes. So basically, the operating system, when it starts a new process, it looks for a symbol called _start. That's what it does. And this symbol _start is usually defined by a C library, by a C runtime library. Usually it's defined in a file called crt0 or crt1.s assembly. So when the C library is constructed, it defines this symbol start, and this symbol start creates argv and argc. It creates those variables. It looks at the special memory region for the environment, creates argc, argv, and calls main with argc and argv. So that's how it works. In this case, we do not have a C library. We do not have a task manager in our class who looks into the elf image and calls start. So who does that? And this is the task of the bootstrap code. That's a piece of assembly that basically calls main. So if you see, it's really simple. So what it does, it defines _start, right? The same as in Linux, and this start has just a jump to reset. So it basically immediately calls the reset function, and the reset function, it branches, so it calls main and hangs. And hang function is just branch to itself, so it's a busy loop. It's basically it's calling.
Does it mean that ARM architecture doesn't have halt machine instruction?
Maybe it does. I don't know. Maybe. Probably it does. But this is the simple, basically bootstrap program that calls main function and then after that resets.
What's up with all the repetitions of hang? Is it a Lyman trick or something?
I don't know why. I stole it from somebody.
Is it interrupt vectors?
Yeah. It's an IDT table. Yes, it's an IDT. I'm not sure is it really needed or not. I'm not sure if this MCU has interrupts enabled, right? I don't think so. I think you need to implement interrupt handling yourself manually. But I guess just in case, on any interrupt, it just hangs. That's it. So if you take a look at the make file for all this thing, so the make file is actually pretty simple. So what it does, and I guess let's just do it. Let's just make. So you see that the make command did several things. Like first, it called assembly. So we cross-compile on my Mac for ARM. So we assembly the bootstrap S into bootstrap O. It will result in like a tiny object file with few functions like _start, reset, and halt. Hang. Then we compile our main.c file without standard library for the Cortex-M0, and that's it. So we compile it object main O. Then we link these two object files using a linker script into the output elf file. And then we just extract the binary side of blink elf into blink bin. And that's it. So blink bin is actually our firmware. Then later on, what we do with the flash command. So make flash. So make flash, basically what it does, it just calls stflash, right? Blink.bin into this special address. And this is the output of stflash. It says, well, trying to find whatever, my development board. Yeah, I found it. Attempting to write, blah, blah, blah. It did. So size 12 to 12, so it's 200 bytes. And that's it. So it says written, everything is fine, and it's blinking. And another bit to look at is the linker ID. So this is a linker script which is used by this linker command. So what it does, it says, ROM, put the program memory, my program, into offset 80000, whatever, and put the RAM into another offset. So put my text and read-only data into ROM, and the BSS, it's initialized data into RAM. That's it. Really simple linker script. And why it is like that special address 80008? That special address comes from the datasheet as well. Because if you look at the datasheet at the map, I guess somewhere it says that the offset for the program is 800 something. I don't know where it is, but yeah, here it is, flash memory. So basically, you see that the flash memory of this MCU is mapped to this memory location. So that's why we link and build our program with this offset. And then when the flash starts executing, like we have correct addresses in our firmware. So that's basically the number where the number comes from. And I guess this is pretty much it. I believe I don't have anything. But yeah, thanks everybody for watching. Questions? Yeah.
Can you just change the program to make it link with a different interval?
Yeah, sure.
Just duplicate the second one.
Yeah, sure. So, for example, here what we have is the delay is 1 shifted by 18, right? So how much is that? I don't know. Yeah, let's make it 2 times bigger, right? So 1 shifted by 19, so that the blinking should be now 2 times slower. So make flash. Yeah, so here slower 2 times, or make it fast, say 16. Now it's like really fast. Yeah.
I thought you were going to show us.
16 and 19.
Yeah.
I thought you were going to show us Mario on that nice display.
Just make it 18. Like usually the next step is to make the UART working. So you would like to see some string output to your terminal, right? So basically you can talk to the MCU over this like UART link. So you can really like send strings and then receive results. Say you can create some sort of say JSON RPC server, for example, right? So you can put a server on the MCU where you can ask peripherals and sensors with some values and make a JSON RPC server, and you send a JSON request like call function get data, right? You'll get a result. Here's your data, your temperature, whatever is this and this. Usually that's the next step, and then the next step then could be something else. Put it on the network. Right? So attach the Ethernet to it, like on this board from this is NXP board. I think it's a company from Netherlands. So this board has a built-in Ethernet chip, so you can talk straight away to the network. Other boards like this one have a Wi-Fi chip, or this is ESP32 Pico D chip. So they have a Wi-Fi transceiver inside this little black box, so they can.
So the device like that, do you get a full TCP stack in the SDK for it, or do you?
That's right. Yeah. Yeah. So, for example, this guy not just has a TCP/IP stack, but also has embed TLS, so it's like secure. Also, the chip itself has capabilities like flash encryption, secure boot, so you can make it a secure product, talking like TLS, HTTPS, whatever.
Can you run Mongoose on this stuff?
Yeah, that's what it, yeah, sure. Sure. Basically, all these chips that I have, they run Mongoose. Yeah, that's, yeah. But usually when I get to, to know some certain chip, I start from the very basic like this, just to get some feeling of the hardware. Some people are like really crazy. They do everything themselves in hardware. They go and find bugs into the SDKs. They find bugs in the documentation. So they say, guys, you have in that table you have like your number wrong. They prove it, yeah.
Do vendors tend to ship C++ compilers?
Yeah, many do. So this GCC, I'm using GCC. You can compile like C++ programs on these guys. Some, ARM. So ARM is a big company who they started back in 90s or 80s. So that was a company in England, and they were doing design. So they were microprocessor design. So they were guys who were creating hardware, hardware design for microprocessor, and they managed to create really good designs for low power microprocessors. And other people, other companies started to buy the designs from them. So now pretty much so you guys have mobile phones. I guarantee you, each of those has ARM processor on it. Most of these boards, they are ARM based. So this British company, their business was to license every design that goes into the end chip. For example, say Samsung. Samsung created their phone. In their phone, they use ARM processor design. ARM does not produce the iron. They does not produce the chip. They produce only the design, a piece of paper, basically. So, but Samsung has to pay, I think the price is 5 or 10 cents for every single device that they ship. So, and you can imagine how much. So ARM was had a huge capitalization. A few years ago, 1 year ago, they were bought by 30 billion, I believe. It's a Japanese SoftBank group. So, and basically, pretty much majority of embedded devices, like something like 90-95%, they have ARM. And ARM itself, they are now trying to dominate software market as well. So they created, so they are now pretty much in all physical embedded stuff, and they starting to create a software stack to attract all vendors to their software as well. So to let them rid of their own SDKs and put on ARM's SDK. And also they started to spin their own cloud, like Amazon and Google. They didn't do that before, but they have huge money, but they are starting to do that now. And their SDK is purely C++. So they have their own operating system called Embedded OS. It's purely C++ running down. So yeah, that's the yes. All right. Any more questions? Or we are done? Cool. Thanks very much. Thank you.